Good day, everyone. It's Don Cooper here from Innovator. We're just waiting for all the attendees to be added to the webinar, and we'll get started. So just bear with us for the next 30 seconds, 60 seconds while the room fills up, and then we'll get on with the presentation. And I'm already getting chats. Hello, Mr. Phil Patterson. How are you? Okay. People are still joining, so I want to make sure we give them a minute or two to start. We had more than 100 people register to attend, and I think we had about 110 as of a few minutes ago. So we have about half of those people have arrived. So I'm just going to give it another 30 seconds before we get started, just so we allow everyone a chance to catch the beginning and the introductions. Hope everyone has a glass of water or a cup of coffee in front of them. I have both. I'm just going to wait till 9:03 and then we'll get started because there are still people arriving. Yeah, Phil says it's too late. Oh, it's Ross, actually. Ross is on here as well. Ross says it's too late for coffee in the UK. Hot tea here in Aberdeen. Yeah, I hear you. It's a Thursday afternoon in Aberdeen. Coffee will keep you awake if you drink it after too much later in the afternoon, particularly if you drink it like strong dark coffee like me. Well, you can wait until after the webinar to have a beer, Phil. Okay, folks, let's get going. We've got just about 60 people here so far, and hopefully we'll get some more people attending, which is kind of some people come and go throughout the presentation, and we're used to that. So welcome to the next episode in the Innovator webinar series. Really appreciate everyone joining, and equally, I know there's from the people who registered, there's a lot of people who've come back for each of our webinars, and hopefully that's an indication that we're giving you some value. We've been trying to do one webinar every week throughout all of this COVID lockdown to be able to provide value and some education-based content for our customers and our followers out there. So I really appreciate everyone continuing to come back. We have 4 more webinars that we are doing throughout June. So hopefully we'll be able to continue to give you some more value and share a variety of insights with you. Today, we are talking about engineered composite pipe repair. And specifically, we're talking with our friends at ICR about their range of composite repair products known as TechnoWrap. Today, I have 2 guests with me. So for those of you who don't know me, I'm Don Cooper. I'm the CEO and founder of Innovator. This webinar is near and dear to my heart. I've been an advocate for engineered composite pipe repair as an approved method for maintenance and repair strategies in Canada for 20 years now. One of the founding principles when I started Innovator 11 years ago was to seek multi-jurisdictional recognition and approval of a controlled engineered composite repair approach to pipe repair. And while that hasn't been fully accomplished yet, we are well on the way with that process, and we'll share some of that progress with you throughout the webinar. But we have a couple of great guests with us from ICR. If you were on our presentation a couple of weeks ago relative to quick flange, you'll be familiar now with the name ICR. So today I have Shona McKenzie as one of our panelists. She is the head of sales, global sales for ICR, and Shona specializes in TechnoWrap. And we also have ICR's Engineering Technical Authority, Gareth, with us. So welcome, Shona, and welcome, Gareth.
Thank you. Thanks for having us both.
Why don't you quickly give each of you give a quick introduction on your background and on your role within ICR and specifically around composites.
Yeah, no problem. So as Don said, I'm Shona McKenzie. I'm the Global Head of Sales at ICR. I've been with the company around about 5 years now. I've sort of worked in a number of different divisions, but the composite repair division has always been the main part of the business that I've worked in. We are a global company, and so I support all of the different global regions that we have, as well as our partners, which we have, again, across the globe.
How about you, Gareth?
Yep, so I'm Gareth Ruccolo. I'm the Engineering Technical Authority for the composite repair sector of ICR. I've been at ICR now just over 5 years, and I've been involved with composite materials for getting on 15 years now in various industries, but finally settled on the pipe work and structural component repair side of things.
Well, when I was looking at your profile, Gareth, I saw that you did a Bachelor of Science and you had a specialty in composite materials.
Yes, I do. Yeah, it started off as motorsports engineering and then moved from the motorsports sector into aerospace, defense, and then finally oil and gas.
My spidey senses are right, I hear two very distinct accents. My wife is from Aberdeen, so I can spot Shona's accent from 10 miles away as an Aberdonian accent, but I don't think you're Scottish, are you, Gareth?
No, I'm from Yorkshire down in England.
Okay. We won't hold that against you, okay?
Very kind of you.
Being Scottish, I might hold it against him.
Well, yeah. So I mean, I'm used to that in my household. That you know, if you're inside of the UK, you guys are allowed to fight, and then you all fight together when you're outside of the UK. It's like you're Scottish and English when you're inside the border, and you're British when you're overseas, right?
We get along with everyone.
Unless it's a football match.
Yeah.
All right, well, let's get on with the show and talk about today's agenda. So let me see if I can advance the slides here for people. So today's agenda, we're going to talk about a variety of applications in composite repair. We're specifically going to share some of the information on the various TechnoWrap products. We're going to dive into the various international standards and approvals that specifically that TechnoWrap have in place, but also just a general discussion on the variety of codes that are already in place to provide guidance for composite repair. And we'll touch a little bit on the progress and the various strategies that are being used in Canada onshore. We're going to share about compliance testing and adhesion, a variety of other types of testing that TechnoWrap and ICR use to validate their solutions. Some design scenarios specifically around piping and pipelines. We're going to look at design life and temperature effects, and then we're going to share some case studies with you. Now, as an audience, similar to our other webinars, you know, we have a few asks of you. Right now, before we jump in, if I could ask everyone who's attending And there's a lot of us here today. I think this is our biggest crowd so far in our webinar series. If you could go into the chat and just type in who you are, where you're from, and how long you have been involved in piping repairs or in reliability. So we're just going to give everyone, I'm monitoring the chat here, we'll give everyone a few moments to go into the chat feature, type who you are, where you're from, and how long you've been in piping repairs and reliability. So we've got people, obviously, some of our colleagues from Aberdeen, Scotland. We've got Derek all the way from Trinidad. Welcome, Derek. Nice to see you again. We've got Rick from here in Edmonton in reliability engineering for 12 years. Fort Saskatchewan, British Columbia, Canada. We've got some people from, I'm not sure where Tamer's from. He's saying Egypt, Canada, Indonesia, Brunei. You're a busy person. Edmonton, we've got David from Sarnia. So we've got a wide selection of people. Lots of our clients on here from various companies all over. Sherritt, Shell, Synovus, Suncor, CNRL. That's fantastic. We got a great selection of people here. I think we have in excess now of 70 people here. So almost every major operator looks like they're represented. That's fantastic. Thank you for participating, and if you haven't already typed in, just continue to add to chat. We love to see the width and the breadth and depth of our audience, and hopefully we're capturing the right kinds of people. So as we go through the presentation, what I'm going to ask is ask questions. For a lot of this presentation, Shona and Gareth will be presenting. I'll come off camera, but I'll have my mic on, and I'll be monitoring chat so that as you're seeing the presentation, if questions pop up, put them into chat, and then I'll interject and add them into the discussion so that we're trying our best to add, give you answers along the way. Feel free to participate in the chat and just make comments along the way. You can also, in addition to chat, commenting in chat directly to the entire group, you can reach out to other people who are in attendance and make comments to them as well. So feel free to use chat to talk to each other and to list to all the panelists as well. And please stay till the end. We'll give you some links with some additional resources on our work on composite repair. Links to be able to reach us and ask questions later, data sheets, getting some PDFs at the end. And our team has also put together a detailed 50-page technical brief on composite repair. And at the end, you'll get the links to be able to get a lot of those resources. So please stick around. All right, let's moving on here. A little bit of lag time. So I want to just quickly kind of frame from my perspective and why I'm a big advocate for composite repair and have been long before people knew what it was. I think I started using composite repair technologies in about 1997. And it has come a long way in terms of engineering standards and in terms of testing and product design. And we are almost at a place in Canada where we can use this as a mainstream repair across multiple pressure components. We're not quite there yet, but we are working hard to get there. But the kinds of things that you're going to be seeing or be faced with as a reliability engineer or as a piping maintenance person is the time and budget associated with piping replacements. Right now, all of our clients are under extreme budgetary pressures with the combination of reduced demand, pipeline capacity, world commodity pricing, the ongoing or the recent price war, and obviously COVID-19. And we just don't have the money or the revenues coming in that can justify all the piping replacements that we often want. We all have aging assets. When I look around Canada and look at the refinery and the upgrader and chemical processing base, many of those facilities have been were built in the 70s and 80s, and they are now 20, 30, and 40 plus years old. And so we have an aging asset base outside of the Northwest upgrader that was recently built in North America. The last refinery to be built before that was in the 1970s. Obviously, we have chemical plants and upgraders that have been built throughout the 90s and 2000s. But we do face a ton of external corrosion and just as much corrosion under insulation, all of which are constantly deteriorating our piping assets. Many of our processes, particularly in the heavy oil districts, have a lot of suspended solids and a lot of corrosive internal corrosion and erosion that we're facing every day. There's significant time that you as a reliability engineer are facing in terms of the time to seek design, approval, installation of leak containment devices. And sometimes and often you want to have a faster way to be able to repair piping that's vulnerable. There's also a lot of composite. You all face a challenge of understanding composite and historical misuse. There's a lot of people out there who have used composite as a Band-Aid, and so there's a perception that it's not an engineered solution, and there are actually a lot of people out there who use it in that manner and don't use it according to ISO and ASME guidelines in terms of the appropriate engineering, surface preparation, and use as a solid engineered solution. So there's a lot of misunderstandings around what composite is because of its historical misuse. And I've seen a lot of that, even most recently with a lot of our promotion of composite solutions. I've seen comments where people saying, well, yeah, we've used it, but it doesn't work. We've used it and it didn't stop the leak. And, the reason for that is they were installing composite over an active leak and didn't mitigate the leak first. So there's just a lot of reasons why we want to really get the information out on why how to use composite properly, how to engineer it properly, how to install it properly so that it is a robust engineered solution for you in maintaining your assets. And there's a lot of perceptions out there of it being a quick fix, and that comes from a lot of historical incorrect uses of composite. And then finally, particularly in Canada, there's a challenge of local pressure authority approval and acceptance, and it's for a lot of the same reasons that I mentioned around historical misuse, that we haven't yet gotten solid recognition with all of our pressure authorities on a systematic step-by-step way that we're going to engineer and install and get the right competency of our installers all qualified in the same way we would do any other pressure component repair. There's a lot of progress being made on that, and we'll talk a little bit about that as we go in. So that leaves it, that's the end of my piece for the beginning. I'm going to hand it over to Shona and Gareth to get on with the show. I'll control the slides in the background, Shona, and I'll let you guys jump in here and just let me know whenever you want the slides to move forward.
Perfect. Okay, so I'm going to kick off, and then I'm going to hand over to Gareth for the more technical section. So I'll leave that bit to him. So I think, Don, you framed that really nicely in terms of some of the issues that people have had with composite repairs in the past, and it's something that we've seen a lot of as well, as unfortunately is the misuse of composite repairs. What I'm going to do is I'll just frame a little bit of the background of composite repairs, a little bit about who we are and some of the benefits. What I'll do is I'll talk through some of our product range, and then I'll hand over to Gareth, who will take you through some of the technical detail. So I'm sure there's a mix of different levels of understanding of composite, so I'll take it back to the basics. So a composite repair is used to restore the serviceability of pressure systems or pipelines or structural components that historically have been damaged or maybe weakened by corrosion. So what they allow operators to do is extend the production life of their plant or asset. The Technowrap brand itself has been around since '92, so we have long over 20 years of in-service history of the product. So not only do we have a big portfolio of operators that we work with, of which most of the operators on here today, we work with all over the world, so it's great to have some of that experience here. We also have a really good track record of installations, so we have about 25,000 installations worldwide, and that is only the installations that we have applied with our own technicians. So if you think of all of the third-party applicators that we have trained, that number is probably significantly more. So looking at what is a composite repair, essentially it's a combination of glass fiber or carbon fiber stitched cloth, which is combined with two-part epoxy resin systems. And that resin system can vary dependent on the application requirements themselves. It's a hand wet layup system, so that means that it's very straightforward if you follow a procedure and you've had training. That's important, and I'll come on to that in a minute. But it's very straightforward to apply if you have the knowledge and experience. And then obviously once it has been applied, it is then pressure containing once it has been fully cured. Some of the comments that Don had previously, we can talk to those with some of the benefits. So for example, if you look at targeted and selective repair of composites, this is one of the huge benefits. So rather than having to replace huge long runs of pipe work, we can target areas where there's maybe pitting or corrosion, for instance, that just need to be repaired in a smaller area. So it can be much more cost effective. Composite repairs are also suitable for all sorts of different defect types, and again we'll come on to that further into the presentation. But the main benefit of composite repairs is that they can be used to extend asset life for anything up to 20 years. And it's not us that says 20 years, that is dictated by the ISO standards. So I'm not saying that every repair will be suitable for 20-year application, but it does mean that we can tailor our response to the requirement of the operator, for instance. So if they are looking for a 5-year repair, we can tailor that repair specifically to that. Again, Don, you mentioned this previously, but there's been a lot of history with misuse in composite repairs. One of the things that we really take pride in is our engineering capability. We offer fully bespoke engineering packages with all of our repairs. There are temporary type solutions that you can apply that are like a bandage, for instance, a polyurethane type bandage. We do offer those services, and that can be used for application offshore by any installer, essentially. However, the solution that we offer is fully bespoke and engineered. So the client requirements are dictated to us, and the application is then either applied by our own trained technicians or our partner technicians who have been fully trained and certified to apply that. Again, some of the other benefits, and there's quite a lot of benefits, obviously, not just thinking about cost and safety. You know, there's the reduction of hot work, which is a big factor, and also that they can be applied live with no requirement to shut down. Again, obviously, this leads to significant cost savings because you're not having to shut down or isolate the plant, and it means that you can actually extend the life of that particular plant or asset. So I'm just going to skip on to the next slide, and hopefully there should be a video that I can run. And this is just an application video that we have. So it just shows you
with
the
this
basic.
one, I'll run the video on my end. Now, I did notice I wasn't sure if this video had to have sound or if you were walking through it. There wasn't any sound on it when I was playing it earlier this morning.
No, that's fine. I'll just talk through the
Great.
application. There shouldn't be any sound. Okay, so a basic installation of composite repairs requires a surface preparation element at the start, so that's not included in this video. So we've assumed that this pipe's been blasted, and that what we do is we use the acetone wash to clean off any debris on the pipework, and then we prime it using an adhesive primer. And what we do is we wet the resin system into the cloth itself. So that resin system is in two parts, part A and part B, and they're combined and measured in the right quantities. It's wet into the cloth, and then that is applied over the pipework. Then what we do is we apply a layer of peel ply, which is the green stuff that you can see there, and that is to allow for the application of the next layers, to ensure that there's good adhesion of the next layers. What we then do is we apply over the top of that the stricture, and this is applied from the middle, and we work that all the way along the composite itself, and that pushes out any of the sort of additional resin system that's not required, and it removes any air pockets that might be within the composite itself. Now, not all repair providers will apply their layers in stages, so we tend to do 2 layers as the first application, and then we do a compression in between layers. We'll do a sort of low load cure in between, so not a full cure, but just enough to make sure that there's no air pockets in between and that we've got good compression between the layers. So it essentially just promotes a better quality adhesive, essentially, through the layers of the composite. Just showing you the video again, but it's relatively straightforward, and if you can imagine, as I said, it's wet layup, so it can form really into any geometry. So whether that is a straight, a bend, a T, you know, we can account for all different geometries of pipework, which makes it a very simple and easy installation. I guess the other benefit being that it's so lightweight, it can be used and moved anywhere. So this is an example of some of the common uses that we have. The great benefit of composite repairs is that they can be used in so many scenarios. That doesn't mean to say that we will accept every repair. There are of course limitations to composites. So if it's not the right scenario for us, we will turn down the job. It does have to be suitable for that application. But the bread and butter for us is your standard hydrocarbon and utility piping systems in all sorts of different geometries. We also do pipeline repairs and caissons and risers, and that can be both leak sealing capacity or for adding additional strength. And we also do underwater curing resin system applications as well. So you can see in that photo at the bottom there, there's a subsea application there too. Go on to the next slide, Dawn. So taking composites a little bit further, there are of course pressure system type repairs, but we also considered all sorts of different repairs for structural components as well. So whether that is decks, tanks, roofs, cladding, beams, vessels, you can see that the applications are, you know, there's so many different applications that can be used for composite repairs. It's a variety of options.
Just to answer a question that just came in here, Shona, Tony Preston asked about bead blasting. Can you just touch, because we didn't show it in the video, can you just elaborate a little bit on the surface prep requirements for
yes, so we're going to come on to the surface prep requirements, but I will quickly touch on it. Obviously, it is the critical success factor of composite repairs. We do require you know, good surface preparation in essentially the landing areas for our composite repairs, as did any composite. SA 2.5, so like grit blasting or sand blasting, is the preferable method of preparation. However, we can also accept mechanical preparation, so ST3 prep, and on very few occasions hand preparation. You just don't get the same quality of adhesion when you use hand preparation, but if it's external corrosion and very sort of low pressure lines, then we may be able to consider it. But Gareth will touch on the technical detail on that further in the presentation.
We've got a variety of other comments coming in that I think we'll be able to cover as we go through on curing time, on temperature, specifically on Jeff Wiseman is asking about ABSA approval. We'll touch on that, Jeff, so please bear with us.
Okay, so I think this answers one of the questions that just popped up anyway. So of course there's limitations with composite repairs. in terms of the pressure limitations, you're looking at around about 3,626 psi. That's on a 12-inch line. Of course, that will vary slightly dependent on the diameter itself. So the smaller the diameter, the higher the pressure it can see, but that's just as a general rule of thumb. If the defect itself is through wall, we are limited to a pressure of around about 725 psi. And that's for a leaking defect. Temperature ranges. So this is an in-service temperature of -100 Fahrenheit to 428 Fahrenheit, or -75 to 220 degrees. So there's a good range of temperatures covered for in-service temperatures there. So looking specifically at our product range, so we have 3 main types of cloth. The one that probably we will talk about most is the triaxial glass fiber cloth. So that's our TechnoWrap 2K. So that is generally used for standard piping systems, hydrocarbon, non-hydrocarbon piping systems. And as I said, that's a triaxial fiberglass cloth, which is combined with our different epoxy resin systems, which you can see listed below, and I'll take you through those. We also have a quadraxial carbon fiber cloth. And again, so that tends to be used for more structural components or when you're considering external loads. And again, combined with any of the different epoxy resins. So essentially what we would do is we would have an application sheet that would be completed. And we would make the assessment as to which cloth type and resin system should be used for that particular instance. So that doesn't have to be decided by the client. So the temperatures, the resin systems themselves, we have the low temperature and high temperature resin. So the low temp is a quick curing resin system at low ambient temperatures. And its in-service temperature, as I mentioned previously, was -100 to 200 Fahrenheit. You have the high temperature resin, which is suitable for in-service of 200 Fahrenheit to 428 Fahrenheit. And that does require post-curing or heat in order to cure the resin. We also have a high ambient resin. And again, that just allows for a longer working life, means that the resin system isn't going to cure off. And it's easier to work with the resin when you've got high ambient conditions. We have a deck repair system. So as simple as it sounds, it's specifically designed for decks. We have within that resin, there's a rubber toughened epoxy, which is suitable for withstanding impact. So it's good for lay down areas or foot traffic, walkways, things like that. So we wouldn't use our standard resin. We would look for something that's a little bit more ductile. We have a glycol resin, which is suitable for methanol and glycol. Splash zone resin, which is a hydrophobic curing resin system, which essentially displaces the water from the surface regularities and allows that to cure either subsea or in high humidities. Or we also use that system for conifer lines as well. And then finally, we have the potable water system, which, as it sounds, we would use that for any drinking water or pot water tanks or pipe work where you have concerns about contamination. That's a bit of an overview of the products that we have. If you can go on to the next slide. So generic types of defects. So we have, we can cover most types of defects essentially. So external corrosion is the standard application for a composite repair. Obviously the application of that composite will prevent any further corrosion. And so the defect size or remaining wall thickness at the time of that installation is used in the design itself. We also can look at internal corrosion and through wall defects or leaks. The thing to consider here is that the composite repair will not stop the internal corrosion. So we would have to assume that internal defect would grow through wall during the life of that repair itself. So if we designed it for, say, 15 years, we would need to understand the rate of corrosion or make some assumptions within that design to assume that that corrosion will continue underneath the composite. And also cracks. So ultimately that depends on the orientation and the loads. So If you think about axial loads, they would obviously continue to propagate out with the sides of the composite repair. If it's in the circumferential position, then it's not such an issue. We can design for a full circumferential slot. And we can also repair mechanical impacts and dents. Okay. So one of the things that we mentioned previously was the standards. So there are 2 applicable standards for composite repairs. The one that we use in the UK is ISO 24817. In America and Canada, I believe it's ASME PCC2. Both essentially very similar in their standards, and they provide guidance on installation requirements, competencies, testing, and the design methodologies that we have. They are, as I mentioned, very similar in the detail within the document. There's not any significant differences. The main difference being the design life. So ASME classifies defects as short and long term, I believe. Gareth, you might want to correct me on that. And ISO is anything up to 20 years, depending on the design conditions. Also, external loadings and temperatures are not considered within the ASME document. Sorry, temperature factors for through-wall defects only is not considered. So basically, as a result of that, the ISO standard gives you a slightly more conservative value when given the same inputs to both. So also off the back of that, we have, sorry, Don, if you could just move on to the next one. We have all of the main types of approvals and third-party assurance. So TechnoWrap has approval and certification from ABS, DMV, and Lloyd's Register, essentially just certifying that we are compliant with the ISO standards.
I'd like to just comment here and just add some some local flavor on the approval process within Canada. I'm not sure if Chris Coombs is still with us. I know Chris had to step away for a few minutes, but I'll give you, oh, there's Chris. Hi, perfect. So a couple things to consider in Canada. So what Shona talked about there, particularly for onshore based facilities, which most of our audience is likely onshore based facilities. You know, there is ASME guidance with ASME PCC2 that provides guidance on the system that all operators and or pressure authorities should use in evaluating composites. Within Canada, there is precedent for approval of composites, and it's specifically within the ZAD 662 CSA standard for pipelines, has clear processes and approvals for composites, and then has been used in the pipeline industry under that guidance for many, many years. Now, as I said earlier in the presentation, sorry, I've been an advocate for getting more facility-based pressure authority recognition and approval for most of my career, but actively since the day I started Innovator, it was one of our guiding principles was to get approval for composites. The progress on that has been one, we were lobbying ABSA and TSSA for a long time. We as a contractor made a little bit of progress there with meetings, but where the progress really started to happen was when owners themselves, the pressure integrity leaders within some major facilities, got on board with us and started to have conversations. That's when we started to see some progress in this area. We have worked with several operators and helped them take all of our processes, procedures, and designs and install them in their own owner-managed programs so that they are ready to both manage that under their own program. So we've helped several operators develop their entire composite section in their own owner-managed programs. And the most positive progress that we've seen now is that ABSA here in Alberta, I think in conjunction with TSASC in Saskatchewan, has now formed an industry working group of both the pressure authorities, the manufacturers of the product, the owner technical authorities, as well as contractors like ourselves. And Chris Coombs, our Innovator's technical director and our general manager, is on that working group. So Chris, why don't you just share where we're at and what are some of the progress that we're making with the Composite working group?
Sure can. Thanks, Don, for that introduction to the group. You really nailed pretty much everything on on the group. So we formed a working group. ABSA is chairing the group, so they're doing an amazing job leading a team of industry, a team of installers and manufacturers, which is really in some cases a team of competitors. And also on the owner side, we have owner representation from most of the main operators in Alberta and Saskatchewan. And within this group, everyone has come together with the common goal of, getting this product or this type of repair accepted under the legislation in Alberta and Saskatchewan. And the way we're doing that is through the creation of an AB document. So people who are familiar with leak repair, I would say there was a creation of an AB document in the last 5 years called AB 521. And what we're doing with Composite is very similar. We're writing our own document, similar to ASME PCC document and similar to the ISO document, but we're writing our own that's specifically applicable to the legislation in Alberta and Saskatchewan. Now we're leveraging the information in those documents. And I can tell you that, under each topic, we're pulling information because those documents are very well written. They're just not specific to our industry. So that's our main goal, is to take different components of our industry, owners, installers, manufacturers, and regulatory bodies, and come together to write that document. We're approximately halfway there. We set a goal to have the document complete at the end of this year. And we have had some delays, especially with the global pandemic with COVID-19. We've had some delays, but our group meets virtually once a month, and we have subgroups working on each individual topic. So we're making great progress. We have a draft document together, and we're continually improving on that document with a goal of having it complete by the end of this year and ready to present to the administrator for acceptance.
Chris, right now, I mean, the end goal, I know that it will evolve with consultation with ABSA and TSAS, but the end goal will be, as I understand it, that there will be obviously standardized, accepted engineering practice that's really guided by existing ISO and ASME protocols that are in place, but owners will be able to establish their own set of composite sections in their owner managed program. And there will be a criteria for certified and competent technicians who will be the only people authorized to install. And there will also be certified and qualified installing contractors. Is that sort of some of the beginning with the end in mind, what we're all trying to accomplish as an industry?
It definitely is, Don. And one of the outstanding items is, finalizing, looking at each repair as a case-by-case basis and deciding, does each repair require a submission? Does each repair require, quote unquote, a CRN, versus establishing a set of criteria that would allow an owner with the right quality management system to utilize an installer with the same level of quality management system, and then furthermore a manufacturer with an approved product to tackle more streamlined repairs. So there's definitely a goal to move away from evaluating each repair on a case-by-case basis. We're not quite there yet, but the idea is definitely to set the criteria for owners, installers, and manufacturers. This document is designed to provide direction, but it's not written step by step to tell you how to do it. One of the terms that we use is the document is not prescriptive. It tells you the goal that you need to achieve, but it's up to the installer or to the owner to write the specifics on how they intend to meet those goals.
Got a few questions coming in as we go through this, Chris. Regan is asking about TSSA. I'll touch on that a little bit, and I'll kind of talk about our strategy. Innovator is constantly introducing new technologies that are not the norm. So, the historical precedent that we have in Canada in similar criteria is with our weldless connections and the ICR quick flange technology. We spent 5 years trying to get ABSA, TSSA, and other technical authorities to approve it based on our standard leak repair and hot tap design criteria, and we really came back to hitting a lot of roadblocks based on had to do a lot of education, a lot of meetings with different technical authorities. And finally, we really found an ASME criteria, which was UG 101 destructive proof testing, that was the criteria for acceptance. So we did that. And then what we found was we either work with ABSA or TSA to get the first round of approvals. And then once that happens, both of those pressure authorities have a lot of collaboration and cross acceptance. So we have talked a lot with TSSA, and we have talked a lot with ABSA, and so we got the ball rolling in the direction with ABSA, and TSAS got on board. So it's collaborative for both of those authorities in the Western Canada oil districts. So we're gonna focus all of our efforts as an industry group in getting ABSA and TSSA protocols in place, and then as soon as that's done, I feel it will be very fast to get TSSA to recognize that. I can't speak for TSSA. I just speak for the fact that we've done this an awful lot, and there is a lot of collaboration and cooperation between the jurisdictions. So once we get, one of those two major authorities on board, then all the other authorities tend to come behind very, very quickly. So that's kind of the progress. A couple of things that I just we're going to offer you some links on the end of this presentation. And this is an opportunity for you as an operator to get ahead of the curve in terms of where we expect and where we're planning to take this as an industry in getting ready. So as I said, there are two things that we really need to be doing as individual owner operators. One is you've got to get a composite plant in your program. So if you wait for ABSA to and the working group to have that ready, then you'll be starting out a year from now trying to get that in place. But we've already done this for several clients. So one of the things that we offer as an engineering service at Innovator is to help you develop your own criteria. We can help you with the processes and all the procedures. So if you would like to start working on your own owner managed program, part of getting ready for industry acceptance, then we're going to be able to help you with that. The other thing that is available because of this ABSA TSAS working group is that group is now allowing us to work with some of our clients on pilot projects of doing this with approvals right now. So we can work with you to start pilot projects as part of this working group. If you want to start to leverage composites today, then we have a pilot project capability. There is an approval process, but we can help you facilitate that. So at the end of the webinar, there'll be a couple of links that you can move forward with us on if you either want to work with us to start developing your criteria, your composite section in your QMS, and if you wish to start to do some pilot projects over the summer and through the fall, then we can also start on those projects with you as well. So those are a couple of really great developments. And so as an industry in Canada, I'm as a 20-year journey of getting composites to a place where it becomes mainstream part of our maintenance and repair set of tools. We're in really great shape, and we're finally in my view, it's been a marathon, and now we're in the sprint in the last 100 meters, and we finally have all industry players on board. So it's really, really great progress. Let's move forward and let Shona and Gareth keep going here on diving into some of the design criteria.
I'm actually going to hand over to Gareth now. He's going to take us through some of the key design details. And then I don't know if we want to answer some of the questions. I think we do cover a fair few of them, but we can pick that up after Gareth if we don't.
Great, thanks, Shona. So I guess over the last few slides, Shona and Don have both mentioned a few key words. So I'm just going to sort of go into those in a little bit more detail. And the first one was the bespoke engineering. So they've already said all of our repairs have got bespoke engineering to support them. But what we need for that is we need to know what inputs to put into that engineering. So obviously things like the pipe diameter, the design pressures, operating conditions, all the design conditions, design lives, defect types, defect sizes, remaining wall thicknesses, any loadings that are going on, whether there's any external loadings in the pipe. So as you can see, there's quite a few design inputs there, which is why we need to do each repair on a bespoke basis, as there's probably no pipe that has all of those exact same conditions anywhere on at least your asset, maybe in the country. And then kind of leading on to the design life of the repair. So for the ISO standard, this sets the figure between 2 and 20 years. For PCC2, again, as Shona mentioned, it gives you a range between short-term and long-term. However, what the range actually indicates is a short-term condition is 2 years and a long-term condition is 20 years as per the ISO standard. So both of them are very closely tied. But what that does mean is, though, for the PCC2 standard, you can actually extend the design life out, obviously as long as the design conditions allow. You can extend it further than 20 years if required. And what this comes down to is the actual strain within the composite. So the composites, the fiberglass will probably have a failure strain of about 2.4%, maybe a carbon of about 1.5 to 2%. And what we do is we derate the allowable strain based on design life. So a short-term repair, so a 2-year repair, for example, would have a higher allowable strain than a longer-term repair, which would have a lower allowable strain. So simply, we're putting a bigger safety factor onto longer-term repairs. And the reason for that is creep in the composite. So what happens is, unlike a steel, the composite actually degrades as a function of load and time. We're not talking here low loads, we're talking if you're holding it up pretty much ultimate failure strain, ultimate failure stress, that you would see the composite begin to creep. So the allowable strain actually decreases as a function of load it's seen and the time it's been applied for. So to relate that back into a pipe, we may be able to offer a very long design life on a repair that's fairly low pressure, but if that pressure starts creeping up and you're seeing maybe that 12-inch pipe, the 250 bar, maybe if that was at 300 bar, you probably wouldn't be able to see a 20-year design life. You may need to decrease the design life to allow the various strains to actually work and the calculations to work. Next slide, please. So when we actually engineer a repair, there's a few questions that we want to ask ourselves. We want to know initially, is the repair strong enough to carry the pressure load? So that's just stress strain calculation, looking at the hoop stress and axial stresses. The next point actually brings in the second keyword that we're kind of looking at, which is adhesion. Adhesion really is probably the most important thing when it comes to a composite repair and using composite materials to fix damaged pipework or structural components. So we want to know, is the repair actually going to remain bonded to the steel? So that's an adhesion check that we do there, which I'll go into in more detail on the next slide. Also, back a slide, please. Thank you.
I was trigger happy there.
Too keen. So yeah, we want to know as well if there's any impact loads there. We want to know, will it withstand the impact? We also want to know, is the repair going to be long enough to transfer any loads into the composite? So we don't just apply these repairs to just the defect. We need to go a certain landing length past the defect itself, simply to get that well bonded zone to enable any load transfer to the composite. And what we get out is when we do the design calculation, we get a repair thickness. So how thick does the composite need to be to take the applied loads? Generally, that's up to about 1 inch thick. We have done some repairs. We've got a few examples at the end where it's getting close to 2 inches thick, but generally they'll come out well less than an inch, normally half an inch or less. Then we want to know, well, then we get the length of the composite beyond the defect. Usually that's around 4 inches either side of the defect. And then you have a taper as well, which is roughly 1 inch as well. So in total, 5 inches either side of the defect is a rough number. Depending on what sort of loads we're seeing, what we're actually trying to fix, we get the material that we want to do the repair with. So as Shona went through before, you've either got the fiberglass, the UK cloth, you've got one of the carbon fiber choices, the SRS cloth or the high pressure pipeline repair system, which is a unidirectional carbon fiber. Generally, where there's external loads, where stiffness is a key driver of the repair solution, we'd use the carbon fiber, simply because the Young's modulus of the carbon fiber is that much higher than the fiberglass. Right, next slide, please. So back to adhesion. As I said, this really is the most important thing when it comes to composite repairs. If we don't bond, you don't transfer load into the composite, therefore the composite isn't actually doing anything, it's not fixing the problem. And the way we quantify adhesion is with an energy release rate. So this is a fraction mechanics technique that we use to basically say what load can you transfer through a bond line without failure. And the way we do this is we calculate it using pressure. So we have a set pipe with various size defects and apply pressure to failure. We can then get the data points and then extrapolate for different scenarios. And as I said, the repair performance is controlled through the adhesion. The more load you can transfer through that bond line, the better the composite will be. And there's a few factors that actually affect the level of adhesion. One of them is a surface preparation, which we've had a few questions on. So that comes down to the cleanliness and the profile that's achieved. I've got a slide on that next. Another one is the actual substrate material itself. So is it carbon steel we're repairing? Is it stainless steel? Is it conifer? Is it a duplex steel? We bond differently to all of those different materials. And then just to add in a few more options, every repair system we have bonds differently as well. So the fiberglass will bond differently to the carbon fiber products. So there's quite a few variables again there. So then back to that bespoke engineering that we offer, they consider all of these different energy release rates, all the different substrate materials, repair systems, the surface prep. There's a huge number of combinations there that we have to account for. Next slide, please. So generally, we would look for a grit or sandblasted surface profile. This gives us the best cleanliness and the roughest, most irregular profile as well. So generally, we would work to an SA 2.5 standard with an average of a 60 micron angular profile. What we're seeing quite often, though, is the grit blasting and FM teams are not available. So we offer bristle blasting. And we downgrade that slightly, even though if you've ever worked with a bristle blaster, you can get SA 2.5. But over a larger area, so circumference of a pipe can be quite a large area, we derate that to an ST3 level of cleanliness and a slightly lower profile as well of 40 microns average. In some circumstances, we can apply on hand prepped profiles, but if you've ever tried using emery paper and files and needle guns, it takes a very long time to even remove a layer of paint. So it can be very difficult to get a very rough profile and a very clean pipe as well. But it may be suitable for low pressure drain lines, but anything more than a bar or two, it wouldn't be suitable whatsoever. So generally always aim for the best, which is the grit or sandblasting to SA 2.5 and 60 microns. Next slide, please.
one of the biggest problems that I've seen with so many clients who try to self-perform this is the surface prep tends to be hand surface prep like what you're mentioning here, and they just don't get a bond, and they then deem that the repair doesn't work, but it was all in the installation process. And we'll touch on active leaks here in a little bit as well, because I know we've had some questions on that.
So this slide sums that up quite nicely. It shows the difference in adhesion that we get for different levels of surface preparation. So the easiest way to interpret this slide is look at a given repair thickness. So if you use the 10 millimeters and draw a vertical line straight up, you'll see that the curve hits probably about 50 bar pressure. This is under one certain design conditions. It's a 25 millimeter hole, 20 years. You'll get a design thickness of 10 millimeters for about 50 bar pressure for grit blasted. If you then reduce the surface preparation to bristle blasted, so ST3, you're roughly at that 10 millimeter repair thickness, you're roughly getting somewhere between 40 and, yeah, probably about 40 bar pressure retention there. So a 20% reduction just from changing to a bristle blasted surface prep from grit blasted. And then the reason that I say we never like hand prep is simply because that the lower black dotted line, for the same repair thickness, you may be getting what, 15 bar pressure retention. So you're seeing a massive reduction, probably 80% reduction in adhesion, just due to the level of surface prep that you're achieving. And obviously we want these repairs to be done properly. Some of them are on safety critical lines. So clearly you want a high level of adhesion, which is why I would always push for the sandblasting or the bristle blasting. Now, Shona did mention earlier that we have a temporary repair offering, polyurethane. The quick fix, it's not an engineered solution, but these red lines just show where that fits in terms of adhesion compared to our engineered solutions. So you can see even for a grit blasted surface profile, with our temporary repair solution, you're lucky if you get 10 bar for the same repair thickness. And then obviously hand preparations hardly even worth thinking about. It's maybe one or 2 bar of pressure retention there. So that's why we always.
This is where a lot of the misinformation and a sort of perception of it being a temporary repair as what I've seen, particularly in Canada and in the United States. This is where this reputation and misunderstanding has come from. The combination of using polyurethane or these water activated what I will call a pipe fitter wrap, along with hand preparation, and then people say, well, they don't work, they just slow the leak down, and that's because that's just it, they don't work. They're not a good solution. They're not an engineered solution. The surface preparation, all of a sudden you get down to basically being able to hold next to no pressure with these solutions. And so the reputation of looking at a piece of material versus the engineering and process that goes behind it is so different in terms of performance. And that's really the educational part of what I want everyone to understand, is that the composite that you think about and what we're talking about are really two whole worlds apart.
Yeah, so I would see the polyurethane as a quick fix, a very, very short-term solution. In terms of short-term, I would say days up to a week or so as a short-term solution. Whereas the engineered repairs, we're saying 20 years, possibly longer, depending on the scenario.
And there are some manufacturers out there who push this product like it is the solution to everything. And quite frankly, the solutions that you're being sold that are these water activated products, and the way that they're being pushed in the industry is like those commercials on television with Flex Spray and Flex Wrap, the stuff you can buy at Canadian Tire. It's no different, and it gets you similar results.
So this slide is fairly similar to the previous slide. It's a slightly different set of inputs, but in this case, what we're doing is we're changing the substrate material. So you can see the top line, what we bond best to is the carbon steel or GRP. We bond pretty well to stainless steel, pretty well to duplex. But then at the lower end of the scale, you've got the conifer and cast iron lines, which we don't bond quite as well to. But the key point of this is it's not whether we bond well or not very well, because conifer generally has much lower pressure seawater duties inside it, so it's not going to quite as high pressures. But what's important is we've carried out the testing to establish the data for each different scenario. So every surface substrate type, we've done different levels of surface preparation, and we've tested our various different repair materials on there. So if you come to me and require a design calculation, we have that data to back up the calculation itself. We have that information, which is very important when obviously you're supplying engineered repairs. Next slide, please. So now we'll move on to a bit of the, I guess, sort of life-size testing or scale testing that we've done on some of our repairs. We've done a huge amount of testing. So this is just a few, I guess, more interesting projects that we've worked on. So this was out for a client out in Milan, and what they wanted was I think this is a 42-inch or 36-inch T-piece, and they wanted several through-wall defects machining into this T-piece. What you might also be able to see is vernier gauges set up at the top and at the side of the T-piece as well. So the intention of the test was actually to see if we could seal up the through-wall defects. But it actually turned out that the spool was designed incorrectly, so there's so much movement in the T-piece itself, hence the vernier gauges that we have there. It was actually moving about 1.5 inches at about 20 bar, so it's flexing so much it was almost breathing, which was quite strange for a test piece. So what you'll see is we've actually wrapped it in carbon fibre. If you've not seen composites before, the carbon fibre is black, whereas the fiberglass is white. And the reason for using the carbon fibre is because it's so much stiffer. It meant we could constrain the movement of the steel and enable it to pass the test. So the test was to pressurise it to 20 bar for 24 hours, then cycle between 2 and 20 bar at 6 cycles per hour for 24 hours. And then it was to take it to failure. And it failed just short of 40 bar. So we got quite a decent reading off that. And we got a good result once we'd actually realised it's constraining the steel and stopping the movement of the steel that was the key to passing this test. Ideally, what they should have done was had a much thicker grade of steel, and then we could have focused purely on leak sealing and stopping the defects leaking themselves rather than looking to add hoop strength into the pipework. Next slide, please. So this is actually at the opposite end of the scale. So this is some small bore pipe work that we actually did for a client in Canada. And this is a 1/2 inch pipe. And there was a very, very localized area of pitting corrosion. It corroded right down to about 0.5 millimeter remaining, and it had a 200 bar design pressure. So what we did was we repaired this, and I believe it was the regulator wanted to see some evidence that composites could perform at higher pressures, because this was, I guess, slightly higher than our usual sort of repair that we do, most about 150 pound systems. So 200 bar was obviously a little bit higher than that. So fair enough to do a test and just demonstrate what happens, where the limits of the composite are and what they could actually do. And as well, this actually landed a little bit outside the ISO standards, simply because of the thickness of the repair. We had to look at radial stresses as well as just hoop and axial stresses. So what we did was simply recreate the repair itself. So as to machine a small area of corrosion into a 1/2 inch pipe, wrap it in composite, and then basically pump the pressure up. And it failed at 1,400 bar. So quite significantly higher than the design pressure. And we estimated it to fail at about 1,000 bar. So we even outperformed our own expectations. And this was about 4 years ago now, and it's actually still in place and still operating as it should. Next slide, please. Thank you. So within the PCC2 standards and the ISO standard, it allows you to qualify high temperature materials without testing them at high temperatures. So basically you can qualify it at room temperature and say it's good up to 220 degrees Celsius. So we thought, well, maybe we should do a test somewhere in between that ambient conditions and the maximum temperature. So what we did was we used our high temperature material. We applied it to a pipe or a spool. We then filled the spool with hot oil at 150 degrees Celsius and submerged it in hot oil at 150 degrees Celsius. We then increased the pressure up until it burst. And if we perform this test at ambient conditions with most of our resins, it will probably burst around 110, 120 bar. Some might go to 130, but usually around 120. This one actually burst at 150 bar. And actually, probably just a side note, when I say burst, it's actually an adhesive failure and you get a very small jet of fluid out the side of the repair. It's not a catastrophic failure or anything like that. It's a very inert failure. So yeah, this one failed at around 150 bar. So it gave actually a higher adhesion value than it would do otherwise at ambient conditions. So what that meant is we actually derate our repairs for higher temperatures. This actually meant we don't need to do that, although we still do that because the standards prescribe it. But it shows that our repairs do perform at high temperatures and they perform very well at high temperatures as well. So next slide, please. So we'll just move on to a few case studies now. Again, these might not be quite applicable to what sort of pipes you have or what repairs you have. But I simply picked a few fairly interesting repairs just to give a broad scope of what repairs we've done in the past, how we've gone about doing it, and what the end result was. So this was an 18-inch hydrocarbon line, and this was internal erosion. So when you have internal erosion or corrosion, the composite doesn't stop the corrosion or the degradation mechanism. So you need to be quite careful with what repair size or what defect size you estimate, because we need to estimate for an end of life scenario. That internal erosion is going to carry on, the defect's going to keep growing. So we need to make a good estimation on that. That's not something we do ourselves, we work with the client. So we would say, or look at what's going on, if there's any similar scenarios on the line that you've had, if there's been any corrosion monitoring over the years. And we'd work together to find a realistic value and a sensible value to use in our engineering. So we'd then carry out all the engineering and the scope would be executed using our fiberglass 2K repair system there, our low temperature resin. I guess we've kind of gone over some of the benefits already, but there's obviously there's a no hot work. We're reinstating the hoop and axial stresses there. We applied it while it was live, and although this one had a 3-year design life, simply because that internal erosion, it can be sort of designed to last longer. Next slide, please. So I believe this is a video of a caisson that we repaired where there was quite a few leaking defects. It was almost leaking like a sieve. There was, I think, about 40 defects along the length of this caisson. As soon as we plugged one, another one leaked. But what's important is we need to ensure that the defects are not leaking at the time of the composite application. So it's very, very important that you plug the defect and you ensure that defect is no longer leaking, as if it is leaking, it will affect the integrity of the engineered repair. So fairly small defects on this, but nonetheless they were tricky to repair with such a high number of them.
Yeah, there's just a few leaks on this one.
Yeah, a few too many, I think.
I've actually seen worse.
So this is just going into a bit more in-depth detail on that previous video with the leaking caisson. So we use quite a few different methods of sealing up the leaks, but the one we found probably the most repeatable was to use small composite plates and use epoxy putty and straps. And what we could do is we could push the epoxy putty into the leaking defects with the straps and the composite plate to get them sealed up. Other areas just had epoxy putty, some areas had rubber bungs applied. It's basically anything that we could do to stem that leak until you get the composite repair applied. And then simply what we did was we applied the composite along the length of the caisson. In some areas there was just fiberglass, other areas there was also carbon fiber used depending on the load scenarios, which section of the caisson it was on, whether it was near the dead weight support or not. Go on to the next slide, please. So this was another caisson. You can see we've obviously used the carbon fiber here. Simply again because of the loads that were going through this section. So there was internal pressure, but there was also bending moments that had to be accounted for. And also the landing lengths were quite limited, certainly in the lower section, because there was a nozzle coming out the back of the larger diameter section. Again, similar sort of benefits to the previous repairs. The no hot work, we could apply it localized just to that area. Changing out that section that was damaged would have been a nightmare because it sat right underneath the flange, so it would have meant changing out the whole T section, which wouldn't have been the easiest. Next slide, please. So this is another caisson that we've repaired. This was in the North Sea. So with caissons, when you actually design and engineer them, the main consideration is the wave loading. So in this case, it's a 100-year wave, which resulted in a 100 kilonewton bending moment, and also 25 kilonewton axial load to be applied. The internal pressure was pretty low, so it wasn't that was driving the repair. It was a huge wave basically slamming into the caisson that we had to design for. And we also, as it was internal erosion, we had to design for separation of the caisson. So again, we had to go slightly outside of the international standards and apply some of our own methods to looking at the adhesion of that caisson and ensuring that simply the inner steel wouldn't slide out the bottom of the composite. And again, something that was slightly different on this was the client wanted us to wrap through lateral guides. So as you've seen in the videos, these composites, they need to be applied by hand, and quite clearly where the lateral guide is situated, you can't physically get your hand to the area to apply the composite. So what we did was we manufactured some steel sleeves, and you could probably just see in the picture in the bottom right hand corner, there is 2 pad eyes either side. So what we did was we supported this just above the lateral guide, wrapped it in composite, had it supported on ropes, wrapped it up in composite, then slid it down through the lateral guide. And you can just see in the top picture, it sticks out very slightly where we've tied the rest of the composite into this section that we slid through the guide. So what that meant was there was full continuity of the composite, the full length of the caisson. So there'd be no external influences on erosion or corrosion. And it would also reinstate the strength along the whole length of the caisson as well. Next one, please. So this repair, again, was actually on a caisson, but what I want to show you here was more some of the, I guess, the more tricky repairs that we've done. So our client very kindly told us this was a pinhole defect, and when our technician got out, it clearly wasn't a pinhole in the slightest. But what was quite difficult about this was one half had the caisson going down to the sea, and this is a nozzle coming off that was fixed. So the sea was actually causing quite a lot of movement over that damaged area. Luckily, again, the pressure was quite low. So what we did was we managed to apply the composite just to the landing areas while the defect still leaked. And then we formed a composite plate, almost like a piece of guttering, that we could bond over that area just to keep the flow going through the nozzle rather than pouring out the side of it. So we had the composite applied to the landing areas. We had this piece of guttering, composite guttering bonded on to stop the flow of water. And then we used our fiberglass to start chasing it into the middle of the repair and eventually overwrapping the whole thing. As there was some fairly significant loads, we then had to apply the carbon fiber on top of that to deal with any loads over the lifetime of the repair. And that was done 2 years ago, and again, that's still in place now and still containing pressure, and it still looks as good as new. Next slide. So this was a section of pipe that we repaired in the Middle East, and trying to keep the cost down for the client, we actually only started off by repairing the T-piece, but as we did more sandblasting, more defects were revealed, but they were much smaller defects. So what it meant was we could engineer the repairs for different locations of the pipe and different defects that we found. So in the T-piece, I believe we had 14 layers. On some of the straight sections, we only had 4 layers of composite, and some of the bends and some of the larger defects were somewhere in between that. So what it meant was we could apply the correct amount of composite or the required amount of composite for the defect that was discovered. I mean, we could have quite easily applied 14 layers over the whole length of pipe, but the costs would have gone through the roof, and we would have had technicians on the asset for a long time. So it made sense to keep it as sort of bespoke as possible and engineered as for each section. And I believe that was about 40 meters of pipe as well that we repaired. And this one was a repair we did in South Africa. And what's slightly different about this one was they had to apply some clamps first to stem that leak. So this was actually carried out, the clamping was carried out by some technicians on the site already, not our technicians. They clamped it up, but then they wanted to get design life. They wanted a fully engineered solution that would last them 10 years. So we then treated the clamps as defect areas. We applied the 10-year design life. So what we actually designed for was a clamp failing. And then, as you can see, we wrapped over the whole area. We achieved really good compression over those areas. You can actually see the bolts almost sort of pushing through the composite there. We got that's such a good level of compression. And that was all applied live as well. So again, it meant they didn't need to do any sort of shutting down or anything. And the final case study now. This was, again, one from the Middle East. And what had happened was they had pressure tested the stainless line about 2 years or a year or two previously with salt water, but it had never been drained. So when they could then bring it into service, all the welds had corroded out. So you can see what we've done here. We've basically gone round and wrapped every single weld in composite. A few of them had clamps on. So the picture in the bottom right, you can see there's a clamp there that we overwrapped. But the picture in the bottom left, you can see that we applied it straight onto the weld. Designed with through-wall defects in mind, that even though some of the welds weren't leaking at this present point in time, they may continue to leak, or they may continue to corrode and then eventually leak within the design life of the repair. So again, this is something we have to speak with the client about, define exactly where the defects will be so we could make sure the wraps are the correct length and the correct thickness for the projected defects. The nature of the corrosion was it was only very small pinholes, so we could design for the full weld actually corroding away. And again, that was done quite a few years ago now. I think that was maybe 7 or 8 years ago. And again, it's still in service and performing exactly as it should. So I think that's everything from me.
Yeah, absolutely. We're going to jump now into Q&A. I'll just say to everyone, webinars are one of the ways that we're trying to share various educational content with you. As these webinars are finished, we're obviously performing these live. They will become available to you and to your colleagues that you want to share with your clients on our website. So they will live on our website and people can view them in the future. It normally takes our team a couple of days to take the recording and get it up on our website. So in the next day or two, you'll be able to view the webinars live. The second way that we're sharing with all of our clients is we have a podcast called the Industrial Innovators Podcast. I think we've got about 7 or 8 episodes up there now. We've got about 10 more that are in backlog that we're going to be posting weekly throughout the summer. But there is also, we've already posted a podcast with myself and Shona on composite repair that you can get from wherever you get your podcasts. I use Apple Podcasts, but I think our team is is posting them on about 7 or 8 different channels. So let's jump into questions. And we have a lot that are in chat. If you have more questions, I'm monitoring chat and I'm monitoring Q&A. So the first question comes from Tony, and he says, how much pressure can be applied to, he calls it the laminate, the composite with the wrap process? And have you looked at vacuum process cures? So I think we've addressed the pressure capabilities. Gareth, can you just confirm?
Yeah, so on pressure, we roughly say 50 bar for through wall defects. Obviously, it really does depend on the size of the defect. That 50 bar is based on about a 1-inch hole with quite a short design life. Obviously, if you've got a huge hole in the pipe, that pressure is going to decrease. And yes, we have looked into vacuum processing, and we do actually do that on some of our repairs. It's best suited for flatter areas, so large diameter tanks is quite well suited to, and flat panels as well. It can be an issue on pipes where you have through wall defects, simply because you're applying vacuum to the composite. You end up drawing air through the defect, so it can be quite tricky in those sort of circumstances. But yes, we've looked into that and use it.
Jeff has a question about live leaks on elbows and how do you execute elbow repairs? Well, for live leaks, Jeff, Innovator is obviously both a composite consulting company. We will help you develop your procedures. Us with our partners, ICR, will provide all the engineering, and we supply the material, and we provide both training and qualified technicians. But we're also a leak repair contractor, and so we have a whole array of ways of stopgaps and leak suspension processes. So we actually have some stopgap high pressure patches that can be applied to elbows to stop those leaks, and then we just treat, once we stop any leak, much like we saw on that multi-leak caisson. Then once the leak is stopped, then you can apply, you can start to engineer and apply the composite solution. So yeah, yes, we can deal with elbows. There was a question on pressure vessels, and can you apply this to pressure vessels, Gareth?
Yes, yep, we certainly can. We've repaired loads of pressure vessels in the past. Yeah, basically treat it as a big pipe.
Exactly, right. There was a question on the 1/2-inch pipe testing that you did, where you created that defect to do the testing for the client. There are lots of defects like that in the field, and the question was, do you fill the void, or do you simply wrap over top of it?
No, we fill the void. We use an epoxy putty. Simply what you need to achieve is you need to achieve load transfer from the bottom of that defect into the composite. So you need a load transfer filler material, which is generally an epoxy putty.
We have a question about, after the composite is, the project is finished, what are the methods to be able to inspect the piping condition underneath the composite? This would be, if it's an external corrosion issue, obviously we stop that external corrosion in its tracks. But if it's internal erosion and you're repairing over top of that, I think there's actually 2 parts to that question. One is, how do you address internal erosion in terms of the repair type, the length of the repair compared to if it was the same defect externally? And then the second question I would have is, what are the options for clients to be able to inspect what's happening to the piping underneath the composite?
Yeah, so I mean, inspection is a huge question, really. But I guess to summarize it as much as possible, X-ray gets through the composite repairs. So as long as it's, I guess, below about 8 inch, you could use radiography to look at the defect area. And there's a company called Sonomatic that uses ultrasonics that can measure the defect and measure steel thickness through the composite. And we've also had a lot of success with pulsed eddy current as well to establish steel thicknesses underneath the composite.
We have a question. I don't believe this is about an active leak. We've kind of addressed that. The question was, can you apply or start the process if the piping is still wet? I'm not sure what the conditions would be when it's wet. I'm assuming that might be in, you know, if it's raining or if it's a seawater splash, but just having wet material, non-leaking, how do you address that?
So we have actually done repairs subsea. So we did one, it was either last year or the year before, at 33 meters depth off the coast of Saudi Arabia. So in that case, yes, we can do repairs to wet pipe. We need to use our splash zone resin in that case, because that then pushes the water away from the steel and ensures you get quite a good bond. But the bond isn't as good as you would get if it was applied to a dry pipe in ideal conditions. So the end result is the pressure containment might not be as high as a brand new, or sort of as a dry pipe.
We've addressed holes. So yeah, so we obviously there has been questions around active leaks. I think we've covered that. There's a question about after sandblasting. So how do you address thickness and sandblasting? You know, what's happening there in terms of how thick do you have to be before you can apply and you can start the process? Not quite sure how to frame that question.
I think maybe, is it maybe in reference to not preparing the defect? So if there's concern that the defect is going to go through wall,
right?
I'm wondering if that's possibly the question. So we wouldn't necessarily have to blast that defect. You know, we could prepare the landing areas and leave that as an unbonded area. Gareth, yes. I don't know if you want to elaborate on that.
Yes, so what we do is we define the defect area as the unprepared surface area. So when we have the clamp example, we don't prepare the clamp, therefore that becomes the defect. If you've got an area you filled with epoxy putty, we don't prepare the epoxy putty, therefore that is now the defect. So if you have a thin wall area of pipe, the last thing you want to do is hit it with a sandblaster and blow a load of holes in it. So we would say we'll treat that whole area as the defect, don't touch it, don't risk creating a through wall defect. We'll engineer that into our calculations, and then the repair can bond on either side of that thin area.
Great. Yeah, we've done lots of repairs where the defect area was very fragile, and we found thicker landing zones on either side to do those kinds of repairs and did them very safely, and they were long-term repairs. Let's see what else we have here. In the question section, once the piping is wrapped, how do you monitor the thickness under the wrap? So we've talked about that. Next question, can you explain in simple terms what is the concept of the repair? Is it dependent on epoxy adherence only, or also there is a preloading, they're mentioning another product, clock spring, preloading it with, so I think the question is the entire repair based on adhesion, or is it also related to the strength in the various layers, the epoxy in the layers? Can you just explain the way that strength is added? You know, obviously we've talked about surface prep and the adhesion. It's deemed a composite because we are effectively, you know, creating bonds between the substrate material and the new composite material as it cures, and it works together to create strength. But just explain to the audience how we are adding strength with each layer.
Yeah,
and obviously the material selection.
Yeah, I guess the answer to that is it's a combination of adhesion and the inherent strength of the material. This sort of question, I'd normally get the whiteboard out and draw a picture. Unfortunately, I can't do that. But simply the composite has strength. So we need to be able to transfer the stress from a thin wall corroded area in the steel into the composite. So I guess one way to think about it, and one way I've explained in the past, is if you imagine those balloons you make balloon animals with, and you wrap some tape around the middle of that long balloon and blow it up, what happens? The middle bit with the tape on holds tight, and the ends of the balloon outside that taped area expand. That's pretty much exactly what we're doing with the composite. We're restraining and adding strength to that damaged area to stop it expanding. And obviously to transfer the load, you need to get through that adhesion. So you need the adhesion there to transfer into the composite, and then the composite can then get loaded and carry load.
Thank you. The next question is, does the repair shrink to the pipe?
No, it doesn't move at all. Once you've applied it and we compress it and it cures, it stays like that.
We've talked about pressure vessels. I'm just trying to see if I have any other questions that, there was a question specifically, I think it's one of our nuclear clients. We have recently been doing some composite repairs with some of our nuclear power plant clients. I don't have the job details in front of me, but they were, I think, on the cold side, the non-radioactive side of the facility. But the question is, do you have any information or any insight into the epoxies or the materials' ability to deal with radioactive exposure?
Yes, we did do some testing with a nuclear power plant in England, Sellafield nuclear plant, and they're also quite heavily involved in some of the work groups. So we have done some testing. Off the top of my head, I can't give you any information, but I can have a look through the test data that we have and see if we can share that.
That would be wonderful. Yeah, I think that would be really helpful with our client who has been, you know, we've had some great success in recent months, and they seem really pleased with composite as a solution at their facility. So as we explore more ways to use that, I think that would be some great insight to see if we can learn what you've done with the on the radioactive side. There was a comment, and I mentioned ZAD 662. And the comment was that ZAD 662 is not within ABSA's domain. It's with the Energy and Utilities Board. And I agree completely. I didn't mean to suggest that ZAD 662 had anything to do with the facility-based pressure authorities. The comment was really to establish that there is already within Canada approval processes in place. And we actually used ZAD 662 as part of our commentary to the pressure authorities to demonstrate that there is already Canadian standards that accept composite, and we weren't just relying on ASME PCC2. So the reference to ZAD 662 was really just about, it was one of the tools we used to start the conversations with our facility pressure authority partners. We talked about void fill, shrinking. I'm seeing if there's any more questions. I don't think we've missed anything. There was
Don, maybe in the top. I think there was a question on how long it takes to cure.
Right.
Ultimately, that depends on ambient conditions as well as the product system that we're using. So ultimately, depending on the temperature or ambient conditions, as I said, it may take longer to cure. You'd be looking, you know, roughly around about up to 4 hours for a low load cure, and anywhere up to around about 24 hours for a final cure. So it can vary ultimately depending on temperatures and product.
Thanks for catching that, Shona. There's a question here I'm seeing. Are you able to fix fish mouth openings of pipe, and how long is the length? Fish mouth obviously is you're preparing for a nozzle on the side of the pipe. I'm not sure what the defect is, but I don't see any reason why if there's a defect on a fish mouth opening and you're tying in a nozzle that we could not engineer that. No different than we could engineer a T or an elbows. I mean, we've looked at multiple complex geometry repairs, and we look at them on a case-by-case basis. The point here is that this is different than just an installation process. The really important part of where our industry is going with composite repair is these are all engineered repairs. So we're not talking about just can we install here and there. All of this is about engineering to be able to give you another tool in your toolbox for maintenance and repair technology. And we're getting to the place where those processes for engineering, review, and approval are going to get standardized so that you'll be able to leverage this with a lot more certainty going forward. We've talked about nuclear. I want to just, I saw a few comments and questions specifically around erosion defects. And Gareth, can you just elaborate on how we treat erosion in terms of how we design the repair versus how we would treat external corrosion in terms of specifically length of repair and how we plan for that?
Yeah, so the key thing is we need to look at the end of life defect size, which none of us have got a crystal ball, so it is quite difficult to predict that. But we need to look into maybe what's causing the erosion, where the erosion is. It could be from fluid flow through the pipe and over a weld, maybe that's causing quite localized erosion, or it could be on a bend or sort of the outside of a T-piece. So we need to look into what the actual end of life defect would look like. We could then calculate a repair based on that end of life scenario, and then that would allow us to actually sort of determine where the repair needs to be. And it could be quite a big, much bigger repair than what you think, simply to account for that much larger defect.
Yeah, the rule of thumb is when you're dealing with internal erosion defects, you're going to expect that the repair to be a larger repair area externally to accommodate for future erosion on whatever that trend line happens to be. There's a question around proprietary nature of the materials. The answer is yes. Each company has their own proprietary design in terms of both the cloths and the variety of epoxies and bonders that we use, and so they are all proprietary. That doesn't mean that you can't buy them. You know, as we talked about, you know, our approach to providing you with capability in composite is fully turnkey. So we'll work with you to develop your own procedures and put them in your manual and help you develop your standards. We will be your engineering consultant to do all of the engineering on your repairs, both standard repairs and custom repairs. One of the clients that has been on the webinar, in addition to helping them with all of their procedures, we also help them develop a lot of standardized repairs as part of their owner managed program. So we did all the engineering for that. Then we're providing the materials to match those design criteria. We can, if you have a program where you're going to want to start to self-perform repairs, we have a training and certification process. We can help you develop all of your documentation and ITP processes for that. And of course, we're also a certified installing organization. So kind of turnkey, all of the different ways that you can leverage the technology from process, procedure, training, engineering, materials, and installation. And we'll work with you in that whole spectrum in terms of the way that you can leverage the technology. It isn't you have to hire us to come do the repair. It could be any one or many of those capabilities. Chris, you had a comment there on some, Rick had made a comment in there. Chris, why don't you comment on that, Chris Coombs? You still here, Chris? There you are.
I am just getting my screen back to where it should be. So I'll touch on the first one. So one of the things that one of the comments that we had was, okay, now we've done, you know, hundreds, thousands of applications industry wide. Are we at a point where we could start publishing, you know, do a study, start publishing some failure rates and investigation into the failure? And from our standpoint, I'm not sure if that's a direction that we would take in publishing a study of that nature, but studies have been performed, especially, and maybe Gareth can fill us in a little bit if he's familiar with it, but in our ABSA working group, we're leveraging a very large study that was performed in the UK on hundreds of applications and the failure within those applications. So that information is not ready for public review just yet, but it has been shared with ABSA. So ABSA is using that information, and as a working group, we're leaning on it to develop the criteria for our document. Once we, I believe that document eventually will be ready for public review, and once we have that, we can certainly share with interested parties that have, you know, taken this webinar, share with you specifically. But until then, we're leveraging the information, but not at a point where we can share it just yet. Gareth, are you familiar with the study that I'm referencing?
Yes, yeah, I've actually been heavily involved in writing that paper with the HSE. And we were the main suppliers of the data into that study. And I believe some of the rough, I mean, I think it's very important that we look at failures and why failures have occurred, because that then allows us to learn from them and put things in place to stop future failures happening. And roughly speaking, I believe it is about 0.1% of repairs fail or don't perform as they should be performing. And of that, I believe it was 75% of those 0.1% were due to the surface preparation being incorrect. The other 25% was down to, or about 24% was down to installation error. And the final 1% of that 0.1% was material problems. So surface prep, we've gone on about it through the whole presentation, but that is the biggest cause of failure by a long way.
Yeah, absolutely. And that's the message that we you know, that's what we took away from that report or from that study in our group. And we're really emphasizing the surface prep technique, you know, whether it's aggregate blasting, whether it's mechanical or hand prep, and ensuring that products are tested with similar techniques that would be used in the field. So we're really trying to leverage the knowledge gained from that study to help us in our legislation here in Alberta.
Yeah.
The other comment that was there, and this is going back to the shrink comment, Gareth. And so I think I'll let you answer it. I believe I know the answer, but basically the comment is, if you apply your wrap to pressure loaded piping, which that's the goal of the product, is to apply it live, so you can minimize any of that downtime or eliminate any of the downtime. So if you apply your product live, and then during the life of the repair, that pressure is then removed from the pipe, how does the composite react in that case? Is there a risk for the bond to break? And would applying composite, would applying like a charged composite, essentially preloaded composite to the pipe, would that perform better?
So I guess, yeah, there is a concern that if the pipe is turned off and the pressure's dropped to zero, the pipe contracts and the composite contracts. Again, it comes back to the adhesion. So we would then look at the tensile stresses at the interface at the bond line. This is something we check on all of our repairs that are applied live. We would check to see what those tensile stresses are, and can the repair actually cope with those tensile stresses. In reality, they're actually very low, because the stiffness of the composite is actually quite a lot lower than the stiffness of the steel. So it tends to move with the steel itself. So if the steel contracts, the composite will generally contract with it. And those tensile stresses in the adhesive layer are very low. Obviously, with much larger pipes, if you've got maybe a 48-inch pipeline at high pressure, that suddenly goes down to zero, then yes, you can see quite high tensile stresses there. But generally, the majority of pipe work, the repair, it's never an issue.
Thanks, folks. We have a question on cost, and so the question is, how does the cost savings look like across different pipe sizes, and do we have case studies? We've done hundreds, probably thousands of composite repair applications in the last in the 11-year history of Innovator, and in my 20 years of doing composite repairs. And so the answer about cost is much like the old proverbial, how long does it take to catch a fish? And it really depends on the length of the repair, the length of life, the materials we use. So we, you know, what we do from a consultation standpoint with our clients is we look at what needs to be repaired. And, you know, we did some very large 36-inch feed water lines in the oil sands recently. And we looked at all of the defects. We had a lot of T's to repair. Then we had some runs of pipe to repair. It was several hundred meters of pipe. And what we looked at, what was the required repair, what was the life that it needed, and in this case, it was trying to get to either 2021 or 2022 in terms of when they had another outage for that main feed water system. And then we compared cost for both using a fiberglass method and a carbon fiber method. And you know, the carbon fiber is more expensive than fiberglass, but what we found in that application for that size and life of repair is from a cost standpoint, we chose to go with carbon fiber because the carbon fiber needed less layers. And even though the material was more expensive in general, there was slightly less material required because of the strength. And the big savings was in installation time. We had significantly fewer layers with carbon fiber, and that labor savings in terms of time made a significant impact. So we'll often present our clients with multiple options in terms of material and cost, and it's a collaborative approach, and it has a lot to do with defined life. How long do you want that repair, and what's the size of the repair? But we work with you to try to figure out what are we trying to accomplish here, and we're looking for strength, we're looking for sound engineering, we're looking for cost effectiveness. Our approach always is improve your safety, improve your cost effectiveness, improve your productivity, and so we look at all of those to come up with the right solution. And you know, another application with similar circumstances might have a different cost because of material and labor selection. I'm looking to see if we have any final questions. I think that covers it. If we haven't, please throw them up there. We talked about erosion. It looks like it. So a few points that you can take now, folks. One is I'm sharing a link on our podcast. If you want to listen to any of our podcasts, and we do have a podcast up there on composite repair, myself and Shona speaking, that you can share with your colleagues. The webinar will be posted soon. If you want to talk to us about an application, meaning you have some places where you want to look at composite repair, or if you want to start working with us to develop your composite procedures in your owner managed program, or if you are interested in being considered for an early pilot project, then go to our website and click on Want to Talk, and click on composite repair, and we'll get in touch with you to talk about pilot projects or helping you develop your procedures in advance of the ABSA working group process. And you know, we are doing composite repairs every day. I think we're in the field doing several in the oil sands today, as a matter of fact. So all of those inquiries can come from Want to Talk. Reach out to us. And if you want to get some more information after this webinar, I'm just going to go to the last slide. You can go to, if you want to learn more, go to info.innovatorind.com/technorep-info. So you can see that on the screen. And my team in the background has shared that link in the chat. From there, you will get a TechnoWrap at a glance PDF. You will join a TechnoWrap educational series. Our team has put together a series of a handful of educational emails specifically on Composite Wrap that you can get over the next week or so. And by going to that link, you'll also get access to this recording of the webinar that you will be able to view later and be able to share with your colleagues. So thank you everyone for attending. I really appreciate it. We are ending on time. Shona, thanks for joining us and adding value. Garrett, thanks again for carrying most of the show. I'm more the guy on the front end of the stage and the back end of the stage, and you guys did everything in the middle, and I appreciate you bringing value to the audience. We had a lot of people here today. I think this was our highest attending webinar, and it must have to do with the British accents, I think.
Thank you very much.
All right.
Yeah, thank you very much.
Folks, wonderful. We're going to end on time with 30 seconds or so left in the 2 hours. So also, if you go to that link, there is a part of that email series is a 50-page technical package on TechnoWrap and composite repair. So it's a very detailed technical package that you'll get in that email series over the next week. So please go to that link, sign up. We won't hound you. It's simply some automated information we're going to feed you over the next week or two, and go to our website and click Want to Talk if you have some applications and want to talk about pilot projects. Thanks very much, folks. It was a pleasure having you again, and we look forward to our next webinar next week, which is on building strong teams using the Kolbe process.